And so last class we actually showed this process with a couple of elements. We used the example of MgO. We said then when magnesium goes into the compound MgO, that it would lose 2 electrons in doing so. And that when oxygen went into the compound MgO, that it would gain 2 electrons in doing so. And so now we have a name for this. An element that loses electrons, we classify that element as being oxidized. An element that gains electrons, we classify that element as being reduced. And so if you're paying attention, those terms, especially reduction, sounds weird because we're saying that a reduction is a gain. And whenever you hear the word reduction, that usually means less. And so why would it be called a reduction if an element gains electrons? We call that a reduction. What is being reduced? The charge. So it's the charge that's being reduced. So another way of understanding it is that the charge increases in an oxidation. That means it goes up. And in a reduction, it is actually the charge that decreases, which we now call the charge's oxidation number so that we can include covalent compounds. So if the charge or the oxidation number increases, we know that that is actually an oxidation. Welcome back, Daria. And if the charge or the oxidation number decreases, we call that a reduction. So it's really a reduction of the charge. The charge is getting more negative, which is a result of gaining electrons. And so the tricky thing here is you've got to remember that electrons are negative. And so if you're gaining electrons, you're actually gaining negative charge. It's called a reduction. And so you're going to want to write this down, and then we'll continue. What we're going to be doing today is we're going to be looking at chemical reactions. We're going to be getting oxidation numbers for all of our reactants and all of our products, and we're going to figure out what's been oxidized and what has been reduced. Give it some time. Once I see that most of you are done, we'll continue. I'm giving about a 20-second heads up at this point that I'm going to go ahead and move forward. Daniel, are you good? Or are you still? Daniel, are you still working? Huh? I got everyone. Just making sure I'm still typing. All right, so this is an acronym that many people use to help them memorize this process, what's going on. And I believe I shared with your class only last class period a different one that a student had shared with me that they like to use. So this is one that many people use. So if you go find YouTube videos, you'll find this one. And you should write it down, the acronym, just so you know what it stands for. Oil rig stands for oxidation is losing. So I'm writing out the word. Oxidation is losing. And reduction is gaining. And like I said, the problem here is because electrons are negative, it's the opposite of what you would think. So that's why when you gain electrons, you actually get a reduction in charge. When you lose electrons, you get an increase in charge, which we call an oxidation. So you should write this down. And then also, I've given you another one last class, OMP. I said it right at the end of class. This is one that a student had made up a long time ago and shared with me that worked for them. And they said that they remembered it as oxidation more positive. Meaning that if you find that going from the reactant side of a chemical reaction to the product side of a chemical reaction, your charge gets more positive, then we would call that an oxidation. So we'll expand on exactly what we're going to do with this shortly. But first, we're just getting down the definitions. What is oxidation? What is reduction? I'm going to go ahead and move forward now. So there are some steps that you will need to follow. So you should write them down at least one time in your notes. You don't have to write them down every time. But these are the steps to figure out what is oxidized and what is reduced in a chemical reaction. So I'll give you some time to write out the steps, and then I'll show you the process. So step one says you figure out the oxidation number for each element on each side of the chemical reaction. And then step two is going to be compare. If you see the charge goes up, we call this oxidation. And if the charge goes down, we call this reduction. Because it's really a reduction of the charge. So once again, I'm going to give you some time to write down the steps, please. And then after I see most of you have gotten the steps written down in the practice question, I'll teach you how to solve it. And once you get the idea, it's going to be the same every example. The only thing that's going to make any questions more difficult than others is how difficult it is to obtain the oxidation number. Once again, I'm giving you some time to write out the steps, and then we're going to take a look at the process. How do we follow through with this? And the first example that you see is the simplest type of example I could give you. All right, so just like balancing equations, we can actually treat this similar to that, where the arrow would be your dividing line between your reactants and your products. And so instead of counting amounts of elements, what you're going to do is you're going to get the charge of each element on each side of the reaction. The charge, also known as the oxidation number. So on the reactant side, so this is the reactant side, remember, and this is the product side. On the reactant side, what is the charge or the oxidation number of potassium? It's a monatomic ion. If they give you the charge is the oxidation number. So the oxidation number of potassium here is +1. And I do want to say that the 2 in front is irrelevant to this process, meaning you would not take this 1 and multiply by 2. Because what you're giving is the charge of each potassium. So you do not consider the coefficients in this process. So far, so good? It's just the charge of potassium on the reactant side is +1. What's the charge of copper on the reactant side? It's in its standard state. Remember last class, we went over those rules. If an element's in its standard state, the charge is always 0. So we would say copper is 0. And so that's the reactant. What we have to do is trace the changes. What's happening as the reaction takes place? Potassium's going from +1 to what? Here, potassium's going to be 0 because this is in its standard state. There's no charge here. It's an element by itself. Elements in their standard state haven't gained or lost electrons. And so potassium on the product side would have a charge of 0. What would copper be on the product side? Don't look at the periodic table, look at the equation. What's copper on the product side? It's what it tells you. If it's an ion, it's literally what's stated here. Remember that was rule 1. Monatomic ions, if they tell you the charge, that is the charge. That is the oxidation number. So this is +2. And so now that you know what the charges are for each element on each side, this is where you do step 2, which is to compare. Look at what happens to potassium. The charge goes from +1 to 0. Is that an increase or a decrease in charge? That's the way to think about it. Does that number go up or does that number go down from 1 to 0? So that's what we would call a decrease, right? Well, what's another name for that? What are we calling that? We're actually calling that reduction. Meaning that it has gained electrons. To go from +1 to 0, you went from a state where potassium has lost an electron to one where, like, if you imagine what's happening, potassium's getting an electron in this process, if that makes sense. So reduction is what's happening. And so what you need to remember is whenever there's a decrease in oxidation number, this means you have a reduction. That's the process, and that's what we would call it. So this is the red part of redox. Once you figure out one, you actually automatically know the other. Because if one element's losing electrons, the other one must be gaining electrons. And if one element's gaining electrons, the other one must be losing electrons because it's a transfer. One gains and one loses. If I lose $5, I give it to something. I give it to someone. And so what's happening to copper here? We know that the oxidation number increases, right? From 0 to +2, that's an increase in number. And if the oxidation number increases, we call that oxidized or oxidation. And so you'll want to write that out. And that's why my one student had memorized it as oxidation more positive because it gets more positive as you go from reactants to products. So if there's an increase in charge, this is always oxidation. And if there is a decrease in charge, like arrow down, this is always a reduction process. every reaction that is redox has to have one oxidation and one reduction. You can't say that you have two oxidations and no reductions. It doesn't make sense. If one gains electrons, the other one must lose electrons. And so I'll leave this up here for you to write down, and then we'll take a look at another example. I'm giving you a little bit more time. We're going to move forward in about 20 seconds. Remember, I'm not going to write the steps each time. In the next examples, I'm literally just going to start working them out. I always show the steps on the first example.
So it's a reduction.
Potassium reduction. Copper has been oxidized. That's the way to understand it. The reaction is redox. Both. But it's asking, what is the element oxidized and what is the element reduced? The element that's reduced is potassium. The element that's oxidized here is copper, to be clear. We'll take a look at another example. All right, let's take a look. Use changes. You don't have to write the all the instructions again because they're going to be the same each time. What element is oxidized and what element is? And what element is reduced? And that's the same question you're going to get in your homework. What element is oxidized? What element is reduced? And so you've got, this is our second example. This is our second reaction. C solid plus O2 gas goes to CO2 gas. So we're going to follow the steps again. The first step, if you'll recall, is to get the oxidation numbers for all the elements on your reactant side and all the elements on your product side. So on your reactant side, what's your first element? Carbon, right? Just reading left to right. What is the charge of carbon here? It's not in a compound. Oh, that would only be possibly true in a compound. Or if the charge was given. Go ahead. You're right. If an element is in its standard state, the way it naturally exists, it has not given away and it has not received electrons. So carbon here should be 0. What should oxygen's charge be? And I know oxygen and the number 0 look very similar, almost the same. I don't write them any different each other. No. O2, is that in a compound? Or is that an element? It's one capital letter. It's an element, right? This is an element. It's one capital letter. So it's an element. Is it in its standard state? Is the next question. Yes. So the answer here would be that its oxidation number is 0 again. So the oxidation number of carbon here is 0, and of oxygen here is 0 as well. For those of you who don't like to write out your work, you should at least track at the top what the oxidation numbers are so you can track the changes. Now you have to do the same thing, but now for the product side. For the product side, you now have to figure out what is the oxidation number of carbon and what is the oxidation number of oxygen. Because carbon dioxide is a compound, you would have to do the same thing we did last class. If you'll recall, what we did last class was I had taught you one of two methods. You would need to know that, first of all, this is a covalent compound. How do we know this is covalent? Both non-metals, right? Both on the right-hand side of the periodic table. That means they can't both be negative because the overall charge of the compound has to be 0. So out of carbon and oxygen, which one would get the negative oxidation number it wants? Oxygen. So oxygen is more electronegative, that's the real reason, than carbon. So oxygen gets negative oxidation number, which I'm calling ON because I don't want to write out all the words. What is the negative oxidation number that oxygen gets? And yes, you do have to know this by heart or by looking at your periodic table. What would it be? 2. Negative 2.
Oh, so the other one, so this oxygen element is going to be 0.
For here or for here? For here? Yes. Because these are in their standard state, they're always 0. But in a compound, that means that there's not, like now the electrons are being traced to move around. And so where are they moving to? They're moving to oxygen. And so what happens to carbon as a result? If oxygen, and we're saying each if you'll recall, there were 2 different ways to figure that out. You could either set up an equation to solve for carbon. You have to solve for carbon to figure out what its charge is. Or you could do the other method, which was the intuitive method, which is to do -2 times 2 is -4. No, the whole thing has to be 0. So carbon has to be +4. We did this exact example last class, if you recall, with CO2. The other method would be to do 1C plus 2O. You're going to see that this is going to end up being a lot of writing, which is why it's not my preference, but it is some people's preference. 1 carbon plus 2 oxygens is a charge of 0, right? Each oxygen is -2. And so carbon minus 4 equals 0. Carbon equals +4 because the +4 moves to the other side. And that would be it. Do you have to write out this work? And actually, it's going to end up, like I said, it's going to be a lot if we do that every time. You can, but you don't have to. What then is the element that's oxidized here? What element is oxidized? Carbon. They can't both be oxidized. Only one can be. It is called redox, and that helps you remember only one can be oxidized and only one can be reduced. One is losing and one is gaining. So this is the element that is oxidized because the number goes up 0 to 4. We're looking at what happens from the reactant side to the product side. Because 4 is a larger number than 0, it's a more positive number than 0, this means that it's been oxidized. And then for oxygen, it goes from 0 to -2. So what is this element? Is it oxidized or reduced? If its charge goes from 0 to -2, what does that state? Reduction, definitely. Or reduced. That element's reduced, and this is a reduction. So it's reduced or reduction. It's oxygen that's reduced and carbon that's oxidized. So you could say carbon is oxidized and oxygen is reduced. Because we're tracing what happens from the reactant side to the product side. Where are the electrons moving to is the question. And going from 0 to -2, this tells us that this is gaining electrons. And the charge ends up being reduced as a result. So that was our second example. What's going to happen is, just like last class, the examples get a little bit more complicated as we go on. And then we have one other thing to learn about oxidation. The best way to learn it, though, is just to practice over and over and over again, because it is one of those things that if you're not paying attention, it gets confusing. So you've got to make sure you kind of try to get it in as much as possible. Same instructions. Let's say example C. You don't have to rewrite the instructions, just the practice question, so you know what to do. This one is 2FeO goes to 2Fe plus O2G. This is our next chemical reaction. All right, so let's take a look at this one. Following the process again, put a little line where you have your arrow. And then you're going to get the charges of your elements on your reactant side and the charges of your elements on your product side. We call those charges oxidation numbers because sometimes they're official charges. If it's ionic compounds, sometimes they're unofficial charges if it's covalent compounds. Here they'll be official charges because this is all either an ionic compound or an element. So, iron. What's the charge of iron on the reactant side? How would we figure that out? For Theo. Iron's not in a known group of the periodic table. It's a transition metal, meaning it could have multiple charges. So how do we know by looking at this what the charge of iron is? What could we use to help us? Dario? Look at oxygen. We know oxygen has to be what number? -2. So if oxygen is negative, then iron has to be what? +2. Yeah. Iron has to be +2. Good so far? Because there's one of each of them. Knowing that oxygen is -2, iron has to be +2. That actually gives me both of my. Yeah. This is the last lesson. That's going to be on the test. It's all together though. Like this is all about chemical reactions. This is the final topic. Yes. Yes, you may. So iron is +2 and oxygen is -2. That actually gave us both of them for the reactant side. Now what about the product side? You have to now find what happens to the charges of the elements because it's telling us what happens to the electrons really. What's the charge of iron and what's the charge of oxygen on the product side? 0 for both, right? Because they're both in their standard state. This is 0 and this is. So now we analyze each of them. And you can either analyze them one at a time or you can look for which one's oxidized and which one's reduced. Whichever way you do it's fine. I see that iron goes from 2 to 0. Is that charge going up or is that charge going down? So if the charge is going down, we say that the charge has been reduced. So this is our reduction. Iron is reduced. So far so good? Oxygen, it goes from -2 to 0. Is that an increase or is that a decrease in charge? From -2 to 0. From -2 to 0? Think of a number line, right? If we go from -2 to 0, that is an increase. So we have an oxidation here. Because the charge is increased. And reduced because the charge or oxidation number has decreased. So you can see where it can be confusing. If the number goes down, reduction. If the number goes up, oxidation. That's how we use the oxidation numbers to tell us what's been oxidized, what's been reduced. It's telling us where the electrons are going. Because oxidation means lose electrons, and reduction means gain electrons. So it's telling us what is gaining the electrons here, and what is losing the electrons here. What is gaining the electrons here is iron. And what is losing the electrons here in this process is oxygen from reactants to products. All right, let's try another one. D. Try this one. See if you can try it yourself. I'll give you a little bit of time. Use changes in oxidation number to figure out what element here has been oxidized and what element here has been reduced. And this is going to be a slight step up, a little bit more complicated because instead of having 2 total elements in your equation here, you've got 3 total elements in your equation. So check it out and see if you can figure it out. I'll give you a few minutes before I start solving. Try to do it yourself first this time. couple of minutes. Check to see if you can try it yourself first and then verify if you get the same answer. All right, so let's go ahead and go over it. I think, yeah. Did you get the oxidation number of magnesium on the reactant side is 0. It's an element in it, standard state. Did you get hydrogen is +1 and chlorine is -1? +1, -1, right? That's what you should have got for your reactant side. On your product side, I always line up my elements to match each other so I can easily see what's going on. What's my charge of magnesium on the product side? It's in an ionic compound, so you go to your periodic table and you find that it's +2. Hydrogen here is 0. And chlorine here is what? -1. This is in an ionic compound. So the reason why this is the next logical example to do is there's actually an element here that is neither oxidized or reduced. What element here is neither oxidized or reduced? Nothing happens to it. Chlorine. So that's not going to be an answer. What element here is oxidized? What are we looking for to happen for it to be oxidized? Magnesium. Because the charge goes up. Remember, charge goes up, I'll just write it again, is oxidized. And if the charge goes down, when we compare left to right, that's what we call reduced. That's what you really have to remember more than anything from this lesson is this right here. And so if the charge goes up, that means that this is being oxidized. So then what's the element that's being reduced here? What element is technically gaining electrons as we go through this process? It would be hydrogen, the other one in question, that there's a movement happening. So because the number goes from 1 to 0, hydrogen's reduced. And actually chlorine has a name, and I'm going to bring it up because if you were to do a further study, this name would be used more often. I didn't teach a full lesson on ionic equations because you don't absolutely have to know it moving forward into further science classes. But chlorine does actually have a name, and nothing happens to it. It's called a spectator, actually. So I'm going to just tell you, if the charge doesn't change, it's called a spectator. What does that mean? Have you ever heard of a spectator before? Like it's something else, like sports? Spectator means like watching, but actually not doing. It's not participating. So believe it or not, chlorine's not participating in this chemical reaction. It's shown on the reactant side and it's shown on the product side, but we could have taken it out. We didn't actually have to include it. So spectator ions are actually not taking part in the chemical reaction. This is called a spectator. And if you look back at the first example, this is an example of something that's not including the spectator ion. If you see it like this, we're just not including the spectator ion. And so I am just going to bring up, and you'll want to write this down. If the charge doesn't change, that actually does have a name. It's called a spectator. And it's really just the same thing as sports. Spectator watches, it's there, but doesn't participate. Not part of the reaction in this case. Present in the solution, but not part of the reaction. All right, we're going to step up another notch. And then I have one more thing to teach you about a redox after that. One more new concept. We're stepping it up one more notch in about 20 seconds. And so what makes questions harder or easier is how difficult or easy it is to get oxidation numbers. So last class's lesson where you learned how to do oxidation numbers was incredibly important as you move to more complex exams. All right, we're gonna go ahead and do this one. This is example 8. This is the final of this type until we talk about the next topic that's involved with this. So write it down. I'll go over it shortly. Does this look more complicated? Got more elements going on here. You got elements in multiple places. Write it down and see if we can figure it out. It says identify what has been oxidized and what has been reduced. Same question. Like I said, what makes the question harder or easier is really just how difficult or easy it is to pull the oxidation. For HNO3, you've got that situation where you've got 3 elements in a compound. If you want to solve in advance of me, you totally can. I'm just giving you some time to write it down. If you want to then check to make sure you've got the idea. Remember, when you're separating, you should separate each element individually. We want to know what the oxidation number of hydrogen is, what the oxidation number of nitrogen is, what the oxidation number of oxygen is, so on and so forth. All right, so write your dividing line if you're following through. And you can beat me to the answer totally if you want to. You can also keep track of your oxidation numbers up here instead of as a chart. It's up to you. But you should keep track some way of knowing what your different oxidation numbers are. I'm using a chart to make it just as clear as possible. I'm going to look at hydrogen first in HNO3. And you may want to recall to yourself from last class, what would we do if we had 3 elements in a compound? We learned about that last class. We need the oxidation number of hydrogen, nitrogen, and oxygen in this compound. How do we get all of them? Are there any that you know off the top of your head that you should know? You should know the first element, and you should know the last element, and you should be solving for the one in the middle. That's what we learned last class. If you have 3 elements, that's what you're supposed to do. So we should actually know that hydrogen is positive 1. And we should know that oxygen is -2, right? And so what would we be solving for here? For nitrogen. So you can either set up a little equation to do that, or you can do that intuitively, but you should be solving for nitrogen. So I'm going to go ahead and set up the equation. So that's 1H plus 1N plus 3 oxygens equals to 0. Then positive 1 plus N plus 3 times -2 equals to 0. So far, so good? Yeah? One plus N minus 6 equals to 0. N minus 5 equals 0, and then add 5 to each side. Either way that you worked it, you should get nitrogen as positive 5. Nitrogen is positive 5, oxygen is -2. That's what we did last class. Then we figure out H and S in this compound. Is hydrogen still positive 1 in the second compound on the reactant side? Yeah, right? This is +1, this is +5, this is -2. This is +1 and sulfur is -2. So you don't have to write hydrogen a second time if it's the same number. But you get sulfurs -2. Hydrogen plus 1 in 2 different compounds here. This is definitely a more complicated example. Probably towards the level 2. If we were to talk about levels, this is a level 2 question for sure. On the product side, I'm going to line up my elements in the same order. Can I figure out my oxidation numbers for each element here? What would be my oxidation number for both of the elements in NO? What would I figure out? Oxygen would be -2, which means nitrogen has to be +2. So you have this is +2 and this is -2. So far so good? We know hydrogen in this compound water is going to be +1 because that's what hydrogen almost always is. And oxygen is -2 again. So hydrogen's +1. Finally, what's sulfur here? 0, because it's by itself. So we would call it 0. It hasn't gained electrons. It has not lost electrons. And so looking at what we have here, are there any spectators we can take out that are definitely not the answer? Hydrogen's a spectator. It's not actually transferring electrons. What else? Oxygen. So definitely not the answer. So you just take out spectators because that's not gaining electrons, that's not losing electrons, so it's not taking place with redox. So then what's happening, or I guess I should ask, what's being oxidized here? Is it the nitrogen or is it the sulfur? Which one? What are we looking for? If I'm asking oxidation, the charge is going up. So that's going to be sulfur. Sulfur is being oxidized. And nitrogen is being, nitrogen is reduced. And so that's the process. Remember, it's going to be one oxidation and one reduction. If there's more elements there, it means they're likely just spectators. They're just there. And so you have to figure out what the oxidation numbers, if something's a spectator or not. And I want to remind you just one more time, don't look at the coefficients at all. You're looking at what the compounds are. It doesn't matter how many of that compound. All right, so there's one more thing about oxidation and reduction that does make it a little bit more confusing, but it's something you have to learn. So there's a couple definitions here you need to write down. I'm going to pause about 20 seconds, and then we'll move forward if you're still writing down the example. So there's one more thing you have to know. Because this is a transfer of electrons, whatever element is being reduced, that means whatever element is gaining electrons from the other element. And so there's one more set of definitions you need to know. Cambridge uses these definitions, which is why I teach them here in this class, and then I teach them again if you take the AICE class. These two. So go ahead and write this down. The substance that loses electrons is also known as the reducing agent. Meaning, the substance that loses electrons loses them to another element. It gives its electrons to another element. It causes the other element, and that's what I wrote in the parentheses. It causes the other substance to actually gain electrons. And so whatever loses electrons, going back to my example of magnesium and oxygen from last class, if magnesium gives its 2 electrons to oxygen, this means that because of magnesium, oxygen is reduced. Because of magnesium, oxygen is reduced. If it wasn't for magnesium, oxygen could not be reduced. So that's why we call magnesium, in the example I used, the reducing agent. And there's going to be an easy way to memorize this as long as you know what oxidation and reduction is. There'll be an easy way to memorize this. And then on the opposing side, the substance that accepts electrons, that gains electrons, is known as the oxidizing agent because it causes the other element to lose electrons. So oxygen in the example I gave would be the oxidizing agent because it took the electrons away from magnesium. It caused magnesium to lose electrons. And so the easy way to memorize this is that if you see the word agent, it's just the opposite. So whatever's oxidized is always the reducing agent because it causes the other element to be reduced. And whatever's reduced is the oxidizing agent. It's just going to be the opposite, which I'll bring up shortly when I have more space on the next slide. So write down the definition, and then I'll give you the easy way. I'll write it down, the easy way to remember it in the next slide. So you've written down the definitions. I'm going to go ahead and move forward to, we have just, I think, one example of this. What I want to write at the top, you should write this down, is whatever is being oxidized is the reducing agent. So whenever you're asked for agent, you just switch it. Whatever is oxidized is the reducing agent. Whatever is being reduced is the oxidizing agent. Like that. And so then we'll do one question like this with a simple example. Identify what element is being oxidized, what element is being reduced, and then what is the oxidizing agent and what is the reducing agent. You should write down this one practice question, and then there's just a couple more things to go over, and then you'll have some practice questions to do for your classwork homework, which once again, you may be able to finish before the end of class, but that doesn't mean rush. Yes? Yeah, go ahead.
Let me just double check that everybody's back.
Yeah, you're good.
It's there. You just have to read it.
Okay. So I'm giving you a little bit of time, write down a question. And so this is actually how your homework or your classwork homework is going to look, is you're going to be asked for what elements oxidized, what elements reduced, and then what is the oxidizing agent, and what is the reducing agent. For, it's like 7 or 8 different examples I have. So let's take a look at what to do. First thing, write your little line. And you can either just track the oxidation numbers above the elements, or you could write it as a chart, whichever way. But you do have to know what is the oxidation number of each element on each side of the chemical reaction. For calcium on the reactant side, I did not include the states, but technically, whether the states are there doesn't really matter. You can figure this out with or without them. What is the oxidation number of calcium? It is an element by itself. It hasn't gained electrons, hasn't lost electrons. Its charge, its oxidation number is always 0 if it's in its standard state. Chlorine on the reactant side is also in its standard state. It's just an element. So it would also be 0. In the product side, calcium is in an ionic compound. So what we get is charge from the periodic table. Calcium would be +2, and chlorine would be -1. So what element is oxidized? and this is the quick thing I want you to just remember. Whatever element is oxidized is the element that gives electrons to the other one, so we call it the reduction agent. So just write oxidized slash reducing agent. Whatever's being oxidized is always the reducing agent. Which means, what element is reduced? So we said the element oxidized is calcium. What element then has to be reduced? Once you know one, you know the other. Because if one is gaining, the other one is losing, and vice versa. So if we said calcium is oxidized, what does that mean about chlorine? Chlorine has to be oxidized or reduced? Reduced. So reduced, and anything that's reduced is known as the oxidizing agent. So we would write that next to it. So that's just how to take care if you're asked for the oxidizing agent. My suggestion is to figure out what's being oxidized, what's being reduced, and then flip it if you're being asked for the agent, because it's asking what is it doing to the other element when it's asking for the agent. All right, there's a couple more ideas we need to cover before we're done. The one thing I wanted to bring up was what you could do to a metal, a highly reactive metal, because the single replacement reactions are actually an example of redox reactions. And the other thing I wanted to bring up was how can you tell just by looking at a chemical reaction if it's actually going to be redox or not? Because when I first brought up redox reactions, I told you that a lot of chemical reactions are redox, but not all of them are actually. And so we will actually be able to look at the 5 classic reactions and tell if they're always redox, sometimes redox, or never redox. And those options are there. So let's go ahead and move forward shortly. Make sure you have this example down though, because this is exactly how your classwork looks. It's just like this. 7 questions like this one, with just different reactions. And like I said, the only thing that makes a question more complicated or less complicated is how difficult it is to get the oxidation numbers. So if you are not good at getting oxidation numbers, then this process might be a struggle. But if you are good at getting oxidation numbers, then this process hopefully will be simple as long as you remember what I taught you today. All right, I'm gonna go ahead and, you don't have to write this down. I just wanted to bring up because it's gonna show up in your lab. If you have the presence of a salt, this actually accelerates corrosion. You'll see this next class because we're gonna do it as one of the laboratory exercises. And it makes electron transfer actually easier when you have the presence of the salt. One way that you can coat a metal to make it not reactive is to put a layer of a less reactive metal on the top. And so if you look at the metal activity series, if you coat with a metal that's not very reactive, like silver or gold, then the metal inside will not be as reactive. And so that's what that says. And so you will want to write this down. If we want to prevent corrosion, this is controlling corrosion, metal corrosion, we can do this by coating the surface of the metal with something that's non-reactive. Something like a less reactive metal on the activity series, or an oil, a paint, a plastic. It says here another metal. I would say a less reactive metal to be specific. Not any metal, a less reactive metal. Reactions of corrosion are redox reactions if it's a metal replacing another metal, or a metal placed in an acid. Like I said, we'll see this in practice next class because one of the labs we're going to do is going to illustrate this. You'll notice that it says these coatings exclude air and water from the surface of the reactive metal. We learned that in the air, what often reacts is oxygen, and that will oxidize substances actually when we add oxygen. And then water can be reactive with certain metals. We also did learn that earlier in this unit. So I'm going to go ahead and go to the last thing you need to know, which is how do we know if a redox reaction is going to happen or not? Because some reactions, chemical reactions, are redox, and some of them are not redox. And so this is the final question. How can we determine if a reaction is redox or not? Like, is this a redox reaction or is this not a redox reaction? So go ahead and write that question down. How can we determine if a reaction is redox or not? All right, so how can we determine if a reaction is redox or not? The simplest answer is you would check to see if any of the oxidation numbers changes. So the quick answer is check if any oxidation numbers have changed. From reactants to products. If the answer is yes, it's redox. If the answer is no, that means not redox. In order for there to be a redox reaction, there has to be a transfer of electrons, which means there has to be a change in oxidation number. The electrons have to be transferred from one element to another. And so if the answer is yes, it's redox. If the answer is no, then it's not redox. That's the simplest way to put it. But it turns out that in our classic chemical reactions, the 5 that we studied throughout this unit, some of them are actually always redox. Some of them are sometimes redox, and some of them are never redox. And so if you know your 5 types of reactions, you could actually predict very quickly if you have a redox reaction or not. And we're going to take a look over them shortly. So go ahead and write this down first, like how to tell, and then we'll take a look how we look at the 5 types of reactions to know what is redox and what is not redox. Yes. Sharpie, yes, I do. Here you go. We're going to go ahead and continue in about 20 seconds. You're still writing? So just looking at the 5 types of chemical reactions. Let's start with number 1, synthesis. Do you think it is always, sometimes, or never redox? Let's take a look at synthesis. If A plus B goes to AB, the answer is sometimes. Yep. So sometimes. I'm going to give you an example of one that is and an example of one that's not. And so one that is, if you have, and this is one of the ones we looked at just a couple of minutes ago, you've got elements by themselves merging into a compound. If you've got elements by themselves merging into a compound, this transfer of electrons will have taken place. And so this is yes, but the oxidation numbers do change.
Like AICE.
If you have this situation, where you have CO2 plus H2O, so you've got a compound plus another compound merging into a more complex compound. This would be no, because the charges of all of these elements don't change. So this is a yes, and this is a no. Synthesis can be, but isn't always, a redox reaction. So the same thing is actually true of decomposition. So for the same reason, decomposition, which is the inverse type of reaction, is also a sometimes, which means you would have to check the numbers to know for sure whether it is going to be redox or not. 3, what was the third type of reaction we studied? There were 5. What was the third type we studied?
Combustion.
Combustion. So combustion is this. CXHY plus O2 goes to CO2 plus H2O. Do you think that is always redox, sometimes redox, or never redox? Because no matter what, you're going to have this oxygen going from 0 to -2. Always. So combustion, that means that you don't necessarily have to do the math to figure out whether it's redox or not, if you know your types of reactions. So this is always. Combustions are always redox. There's always a transfer of electrons happening. All right, good so far? I'll leave this to give you some time, and then we're going to continue to the next example. You can actually analyze all 5 types to figure out if they're redox or not. So, synthesis sometimes, decomposition sometimes, combustion always, and then you've got 4 and 5. Let's look at type 4. Single replacement. So type 4, you know, is single replacement, and we've got this situation. We've got whatever A is plus BC, and then you've got 2 options of what could happen, but there's going to be some kind of swap likely, so you get A, C plus B. Writing out an example, just one that we've seen before. Do you think that this type is sometimes, always, or never redox? Always. Because you're always going to have an element by itself going into an element in a compound, and an element in a compound going to an element by itself. So if there's a single replacement reaction that happens, you are going to get a change in the charge, which means you are going to have redox. You are going to have a transfer of electrons. So single replacements are always redox. So if you can tell you have a single replacement reaction, you can tell you have redox without doing the math, without doing the work. And then finally, type 5, double replacement. What do you think about double? The last one. We're almost done. This is the last example. So you've got the AB plus CB goes to AD plus CB. And remember that the main idea of a double replacement is that you're swapping the ions, but the ions are remaining the same, right? So because you're swapping ions, but the ions are remaining the same, it's actually never. If you can tell you have a double replacement reaction, it is never redox. And so that's why I said you could actually look at the types of reaction, if you know them, and determine quickly without doing the work of oxidation numbers and know that you have redox or not. All right, so that's the end of the part 2 lesson. Like I said, next class I am going to do a little bit of reteaching, although like I said, not to the amount of depth, just for those